Hi, this is Jack Simons from the University of Utah, and I want to talk to you a little bit about the role of theory in chemistry education and the curriculum and in chemistry research. This is a picture of the Salt Lake Valley and the skyline, and this is a web link that you could go to if you want to learn a little bit more about who I am. Now, what does theory mean? Well, from Wikipedia, we learned that in science, which is what we're talking about here, the theory is a mathematical or logical explanation or a testable model capable of predicting future occurrences or observations. So please keep that in mind, because in science, this idea of it's a model that's capable of being tested because it makes predictions about future events. In common usage, of course, the word theory often is used to mean conjecture, an opinion, or a speculation, but that's not the way that we use it in science. In chemistry, theory is a mathematical or logical explanation or model connecting laboratory observations to the behavior of the underlying molecules. And it has to be capable of predicting future observations so we can test it. Let's look at some examples of the theoretical concepts that arise in the classes that we teach at the undergraduate level. And in doing this, I want to point out to you that we theoreticians are often sensitive to this issue because sometimes our colleagues, especially during the, say, 70s through 90s, before theory blossomed and became much more useful and applicable, they would say to us, oh, theory, chemistry is an experimental science. There's too much theory in the undergraduate curriculum. We don't need theory. That's the opinion that a lot of people had. But let's look at some of the undergraduate textbooks to see what their authors think about the role of theory. Now, Cotton and Wilkinson's textbook on inorganic chemistry is a classic example. Now, I understand this is an older book now, but it's one that I used when I was a young student. But if you just look at this, right in the beginning of this inorganic chemistry textbook, we talk about electronic structures of atoms, wave mechanics, chemical bonding, valence bond, molecular orbital. So clearly these people think, because they're putting it right up front in chapter 1, or part 1 of their book, General Theory, that these people think that these theoretical concepts are essential to understanding inorganic chemistry. If we look at an organic chemistry book, here's the one that I used when I was a young punk, Morrison and Boyd's Textbook of Organic Chemistry. Again, you see Chapter 1, Structural Theory, Chemical Bond, Electronic Configuration, Unshared Pairs, Polarity Bonds, Intermolecular Forces. So again, these leading organic chemists writing this well-used textbook believe that these theoretical concepts are important in relating the laboratory data to theoretical concepts. Now, sometimes people, again, raise this issue of that we have too much theory in the curriculum. Here's an article written by a fellow named Ogilvy, who I think is a very good scientist as far as I can tell. In his article in the Journal of Chemical Education, he says, we should change our thinking about the teaching of chemistry, away from atoms and orbitals. Theory applied to molecular structure is unnecessary and irrelevant for the general undergraduate curriculum. Explanations of molecular structures based on orbital and such ilk are not science, are nonsense. It should consequently be discarded, etc., etc. Now, I published an article that was sort of a response to this particular one in the Journal of Chemical Education too. My title of my article is There's No Such Thing as Orbitals, and I actually take the position that I agree with Professor Ogilvy on this. In fact, in my heart, I do agree that probably in the undergraduate chemistry curriculum, we need to get back to making sure that students appreciate the, let's say, tactile and just fundamental things about chemicals. That is, you know, the esters tend to have nice smells that mercaptans often don't. That sodium chloride is not a green gas, but is a solid at room temperature. You know, these kinds of practical understandings of chemistry and chemicals are things that we sometimes do, I think, miss out on. And lecture demonstrations, I think, help to foster a better understanding of these more practical issues. But let me return to this concept that Ogilvy is talking about. Orbitals are not real. And I was basically saying in my response to his article, I said, I agree. Orbitals are just constructs or theoretical models that allow us to think about how electrons move around in the atoms and molecules. But there are other things that aren't real too. For example, bond lengths. Now you say, wait a minute. You telling me the molecules don't have bond lengths? Well, let's think about how do you actually determine bond lengths. For example, in a diatomic molecule, what you do is you measure the rotationally resolved spectrum, vibrational spectrum of a diatomic molecule, which I've indicated here into these P, Q, and R branches. You look at the spacings between these various rotationally specific transitions, and use these formulas that say, oh, the rotational energy of a molecule is h squared jj plus 1, or 8 pi squared times the moment of inertia. Wait a minute. So the spacings then relate to this equation, out of which you get this so-called moment of inertia, reduced mass times r squared, and you evaluate this quantity called r, the bond length. But that bond length is just a number you get out of this fitting the rotational spectrum to this formula. You fit the experiment to a theoretical formula, and you get out a quantity that you call the bond length. Now we know these bond lengths are not static. The molecule's sitting there vibrating. And the bond length at one instant of time is not the same as the bond length at another instant of time. So the point I'm trying to make is that the concept of bond length here is something that really, if you push it harder and harder and harder, you have to realize that really that's just a quantity that comes out of the theoretical interpretation of some experimental data. And the theoretical interpretation involves using some theoretical formulas to calculate some vibrationally average distances between atoms in a molecule. Let's look at another situation. We know from X-ray diffraction, we have these, let's say, crystals. Maybe it's some fancy alpha helix structure like we've gone here in this peptide. But we do an X-ray pattern. We see the X-ray dots there, and we use this formula that's n times the wavelength of the X-ray light is 2d sine theta. D is the spacing between the planes of atoms and the crystals. And out of that, we get some spacing between atoms. But again, that's something that relates to an experimental data set being fit to some theoretical formula, this Bragg diffraction formula. And the idea, basically, that I want to put out here is that distances that you determine by X-ray crystallography measurements are not, in principle, exactly the same as the distances that you obtain from rotationally resolved spectra of molecules. The rotational spectrum has something to do with a 1 over r squared average, some moment of inertia being vibrationally average. In the case of X-rays, they scatter from the inner shell electrons of the atoms, and so the distances between these atoms in the X-ray diffraction experiment relate to distances between inner shells of these atoms as they exist in the crystal. Likewise, another example is when you use nuclear magnetic resonance spectra to study couplings between nuclei that are at various distances away. You say, oh, those couplings vary as 1 over the distance between the nuclei to the 6th power, so the NMR coupling constants between nuclei are really measures of vibrationally averaged 1 over r to the 6th quantities. So rotational spectra, 1 over r squared, X-ray spectra, 1 over distance or distances between inner shell electrons, in NMR, vibrationally averaged 1 over r to the 6th. They're all different. So you say, these distance parameters, they're all different. So what are they real, or none of them, are they all not real? None of them is actually a direct determination of the equilibrium bond length of the molecule, because what is this equilibrium bond length? The molecule doesn't just sit there stationary at Re, it vibrates around that value of Re. Let's look at a couple other examples about what might be and might not be real in molecular behaviors. Sometimes when we want to measure the dissociation energy of a molecule, what we do is we measure the energy spacings between the V equals 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5, etc., etc., etc. We measure these vibrational spacings between neighboring vibrational energy levels, and then we fit these, we make a graph of these vibrational energy spacings versus the vibrational quantum number, and we find that these spacings fall off as the vibrational quantum number increases. That's because the potential is anharmonic, so the spacing between the levels gets smaller and smaller and smaller and smaller. And we have an equation that the spacing between vibrational levels is some quantity that's the fundamental vibrational spacing minus something that depends on this anharmonicity. And what we do is we make this graph, and then we ask at what value of this vibrational quantum number is the spacing equal to 0, and we say, oh, that's the place where the spacing would be 0 right up this asymptote. So we add up all these vibrational spacings, 0 to 1, 1 to 2, 2 to 3, 3 to 4, etc., 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 some of which we can measure, but we can't measure these real high ones, but we use this formula to fit it and figure out what is the maximum value of V, and we add these all up, and the sum of all these delta E's gives us our dissociation energy. Well, that's just still a construct because we had to use this theoretical formula to fit this experimental spacing data to extract this value of what we call the bond dissociation energy, a bond energy. Now, another thing is we know that often chemical reactions, when we plot the logarithm of a rate constant versus 1 over the absolute temperature in Kelvin, sometimes we get these straight lines. Out of that plot, we get what we call an activation energy, the slope of log K versus 1 over T. And we use this to obtain what we call an activation energy. But it's only when we realize that transition state theory, that is, what is that E star? It's just a number. But when we say that we know or we think that transition state theory tells us that E star is the height of the barrier on the potential energy surface that the molecule must surmount for the chemical reaction to occur, that's where we make a connection between the experimentally measured number, that is these rate constants being plotted to extract the number E star, and that experimentally determined number is being used in the theory when we use the transition state theory. So experiment and theory really are going hand in hand here. So my point here on these examples I've tried to illustrate are that experiments do in fact give real data. They give peaks in your spectrum or rates as a function of temperature. But the quantities we obtain by using theoretical formulas to interpret or fit these data are less real. Bond lengths and angles, vibrational frequencies, potential energy curves, molecular orbitals, they're all not real. They're constructs of our imagination, but of course they're still doggone important. Because these theories always involve some approximations, their constructs have intrinsic uncertainties and limitations. Now the problem, of course, is what do you want to do? Just give up and say you don't want to have any of these theories around? Chemists would be lost without these theories because we need them to make the connection between the laboratory data and what we want to think the molecules are doing that gave rise to that data. So I think there's a couple of the problems that people have with theory, though, I think are rooted in a couple of issues here. One is that chemical theory usually involves quantum mechanics. That's because the atoms and molecules, and certainly the electrons, just don't behave classically. They don't obey Newtonian equations. They obey Schrodinger type of quantum equations. And those equations are foreign to a lot of people and bothersome, but that's the way it is. As far as we can tell so far, the nuclei moving, the electrons moving, they obey quantum mechanics. So you better know some quantum mechanics if you want to really understand how theory relates to chemistry in the laboratory. Now the other thing, and this is what I want to turn to address now, is that some people who are somewhat negative of us theoreticians say, oh, you theory people are really trying to replace the experimental study by using theory to simulate the experiment. That's not true. And this is a big misunderstanding a lot of people have, and now I want to go on and try to illustrate this. So far what we talked about is how theory provides equations that connect the laboratory and data to molecular level behavior. Theoretical chemists also do try to simulate molecular behavior by using the Schrodinger equation. Usually when we're dealing with electrons and light nuclei, we have to do that. Sometimes for heavier particles, larger molecules, heavier atoms, they almost behave classically, so we can use Newtonian mechanics to describe their time evolution. And sometimes we do carry out simulations of how the electrons and atoms and molecules move. This is mostly recently, though, because in the early days of theoretical chemistry, these equations just were too complicated and time-consuming to be solved by hand. They just took too much time. But modern and inexpensive computers have changed this situation qualitatively. Now in this slide, which I'm going to skip, I give an example of how to solve for the motion of 1,000 water molecules as a function of time if we know the force law that exists between the water molecules and within a given water molecule, how one OH bond and another OH bond and the HOH angle evolve or undergo evolutionary motion, that we could solve these things. And the main thing I'm trying to say with this slide, which I just, like I said, I want to skip, is that in the old days, we would take everybody on Earth really super long to solve these things. We just couldn't do it. But with the high-speed computers, especially parallel computers, we can actually now do these time evolution propagations within very reasonable timescales. So we're able to carry out these things. So let me just give a couple examples now of how theory is used to simulate molecular behavior, not to replace the experiment, but to help interpret the experiment. Now, in this slide here, what I have is some experimental data that's here, here, and here, actually at the bottom only, that relate to some experiments that Mark Johnson's group at Yale University carried out on the water tetramer anion with some argon atoms attached to it. So what they do is in the gas phase, they form these water tetramer anions with an argon pressure around. They mass select using a mass spectrometer, for example, so H2O4 minus with 5 argon atoms attached. It could be with 1, it could be with 6, could be with 2. But here they're talking about 5. This parent ion, that's water tetramer anion with 5 waters, is then mass selected and isolated. They then shine an infrared laser on this sample and shine it in the frequency range where you would expect vibrational excitation of some of the OH stretching and HOH bending vibrations, or if they deuterate, as they did in this case here, they have deuterium, some OD stretches and DOD bending vibrations. And then what they do is they look for the appearance of species that have lost an argon atom or the disappearance of the parent species that have lost one argon atom. The idea basically is that the vibrational excitation of the underlying H2O4 anion eventually transfers this vibrational energy out of the OH stretch or HOH bend into the argon atoms, degrees of freedom, and boil off one or more argon atoms because they're very, very weakly held. In this so-called action spectrum, where they look for the appearance of ions that have lost an argon as a function of the wavelength of the infrared light they use to excite the HO stretch or the HOH bend motion, they then get essentially an infrared spectrum of the H2O tetramer anion. And the idea basically is they have this spectrum. So they see these peaks, this one here, this one, this one. They don't come out labeled like this, they just come out. And they want to know, well, what is the geometry of this underlying H2O4 minus anion, and what are the vibrational motions that give rise to these various peaks? They don't know that. All they know is they have a species that is H2O4 minus that has a certain number of argon atoms attached to it. They don't know its geometry, and they don't know what these vibrations mean. So what can be done, and they did this in collaboration with a friend of mine, Ken Jordan at University of Pittsburgh, is they can carry out some electronic structure and molecular dynamics simulations of these various H2O4 minus anions at various geometries. So they optimize these geometries looking for local minima on the potential energy hypersurface. They find many of them. Some of them are very high in energy, some are low in energy. And what they've illustrated here is they found that this closed ring structure of the H2O4 minus anion has a vibrational spectrum that is calculated, that is simulated, that is predicted from the electronic structure calculation to have peaks at these frequencies right here, these frequencies right here, whereas this open sort of quasi-linear structure of the H2O4 minus anion is predicted, simulated that is, to have vibrational peaks here, here, and here. And these two structures here are among the low energy isomers of this particular H2O4 minus anion. And the idea basically is that by comparing these theoretical predictions of the vibrational spectrum for the two different structures to the observed vibrational spectrum, they can say, oh, it looks like this predicted spectrum is a lot closer matched to the experimental reality than is this one up here. Therefore, we can conclude, that is, we think, that this structure here, which is what we, the infrared spectrum of what we had in our real instrument, probably arose from this particular molecular geometry. So this is what they would then say is their prediction of the molecular geometry of H2O4 minus anion. Now they couldn't have done that without theory. The theory allowed them to compare the theory to the experiment and make a prediction. Before that, they had no idea of what the structure of that molecule really was. So that's the kind of thing that theory really does. It allows you to look with a really small microscopic microscope, a very small molecular level microscope, at what molecules are doing to give rise to a particular experimentally observed phenomena. Just to illustrate to you the complexity of this kind of situation, this Ken Jordan's group, the fellow I mentioned earlier at University of Pittsburgh, has been studying electrons binding to other water cluster anions, and he finds that, for example, for various size anions, so here's water, I don't even know, 24 I guess it is, there's various kinds of structures of the water 24, all of which bind an electron. That's what this orbital is here. Some of them have the waters arranged in sort of these cubic things, structures with the electron inside, electron outside. Sometimes the electron is solvated with the waters all surrounding it inside. Sometimes the electron's on the surface. So there's many, many different kinds of structures. And if you were therefore carrying out experiments, say on water 24 minus, you really wouldn't know just from a mass spectrometry experiment whether you had this, 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 or this. And the theory can help you interpret, perhaps based upon how strongly this electron is bound to the cluster, which you might measure experimentally, whether you have this one, this one, this one, or that one. So that's the kind of role that theory plays in experiment. Another kind of phenomenon that theory's been playing a pretty big role in interpreting recently is how various cations and anions prefer, in terms of energies and tropics, to exist either near the interface of a water-air interface or into the bulk water. So for example, we have some work here from Pavel Jungwirth's group in collaboration with Heather Allen and Doug Tobias, Liam Dang, and so forth, where they've been studying, for example, sodium chloride, sodium hydroxide, hydrogen bromide, hydrogen chloride, and what they're doing here is to study the propensity of the various cations and anions here, H plus or Br minus, to exist at a interface. So up here is the air, and then here's water. The blue is water. So air, water, air, water, air, water. And they're studying here the density of, for example, the chloride ions, which is this yellow thing here. This is saying basically that the chloride ions tend to have higher density up near the top, near the interface, whereas the sodium ions have higher density a little bit into the bulk. In the case of sodium hydroxide, the hydroxide ion, which is this sort of fuchsia labeled thing, actually is deeper in the bulk than is the sodium ion, which is this green thing. Whereas in case of hydrogen bromide, they find that the bromide ion tends to pile up more on the interface, and the sodium ion, or sorry, in this case it's the proton, more into the bulk. So they've been studying the propensity of cations and anions to distribute themselves spatially within a aqueous environment, either within the bulk or at the water-air interface. This is very important for studying atmospheric chemistry, where you have these nano droplets and various dispersed salts that come maybe from the ocean being blown by air into the atmosphere. So this is a hot topic where theory, because it can watch where the ions are, helps you to understand perhaps what the experiments are telling you. So what's the take-home lesson here? I think that theory and simulations are important ingredients in chemistry because they provide tools, that is, equations or simulations, by which we connect laboratory data to molecular behavior. The simulations are especially powerful because they let us see what the molecules are doing that gives rise to the experimental observation. And by no means does the theory attempt to replace the experiments. It's attempting to help interpret the experimental data primarily. Now, one of the problems, of course, is that theory often is spoken in languages of mathematics and quantum mechanics that we feel uncomfortable with. And I would say to the professors and to the young postdocs and to students, try to get the younger generation people to learn these languages. Take more mathematics and quantum mechanics rather than trying to avoid them and be touchy-feely, because you really can't beat it. Mother Nature's molecules and electrons obey quantum mechanics. I'm sorry, that's the way it is. Well, I hope that you have benefited some from this, and I'm now going to end. Thanks for listening.